I don't do that. I have to use it.
It's like
I mean, I understand the security, but it's just this is why we can't have like.
so that's why like halfway through my day, like, because I was always thinking new.
Yes, that's not true. All these things just like explode.
They explode. Like I was thinking yes, then I was like, even if my then even suddenly August comes in, oh no, my is going. But it's supposed to be this
August, yes, August. That's about the time.
A lot of things happen in August, like the Wi-Fi also more.
Yes.
Yeah.
Oh, yeah, how they mention it? Yeah, the Wi-Fi.
Yeah, that makes a lot much more sense than what. But yeah, isn't it really like so like you're giving this to the like I'm still able to connect to like wire that the SSH to like personal.
Yeah, I guess they're like
Yeah, I hope you do not use it. I need like personal as well. That's true, correct.
Rather than SSH, remote desktop access desktop and then just type of application.
Okay, I tried Chrome remote before, but the thing is that I think it times out after a while.
Okay, everyone, you guys can try to log into Kahoot.
That's kind of hilarious.
Yeah. That's like the most ridiculous thing I've seen.
Also, like when you basically call another function is like something like there's a pattern to straight in. That topic, but
Forgetting these.
Well, do we have the person who created? Yeah, your name again, sir? Suveen. Yeah. Okay, Suveen is going to narrate the Kahoot for us today. We got another, well, let's see, we have 2, 4, 6, 8, 10, 12, 14, 16. We have about 18 people, so I hope all of you do log in. And see how many do we have right now? 10. Give it another 2 minutes, 20 seconds, sorry. Log in. Okay, this song is in there from Mac. All right, I think we're ready to go. So you take it away. Thank you.
The first question, when scaling models, the data size may grow, like in which way in model size while avoiding overfitting? This is like in the slides. So the answer is sublineal. Only 2 people got it correct. I think so that So in a model, when the data size increases, test loss decreases, and it's gonna go to a minimum and stay there. Even like after we increase the data size. So it's sublinear. We all had like 2 people. Then this one's double points, I guess. So which of these are advantages of using flash addition? So the first option is wrong because even if we use flash attention, we have to store the O in matrices. It's only saves us from saving O into the power like n squared matrices. It's the tricky bit.
I think the first question.
Okay, I'm not sure about the explanation to be honest. Like maybe someone the first one.
The first question.
Yeah, the scaling model data size may
Method, right?
yeah sublinear. That one.
Oh, the first question.
Yeah,
You mean like he only increase the model size but not increase the data set size, really?
Yeah, so the like when compared to the model size, the data size should increase in sublinear.
In
And-
sublinear.
Yeah.
What exactly the sublinear is?
There was a value, I think,
Less than.
less than n.
Less than.
that means there's still some sort of like small curves and
Oh.
hints in it. So like if you look at like the like zoom in this or something.
Yeah, you can share it on the Slack, the animal channel. That's everyone can access that.
We have hoopy leading here. It's from double points. Yeah. Shall I go to the next question?
Yeah, I think we can find the answer to the first one.
Yeah.
Which,
Which parallelism approach is depicted in this diagram? So this one G5, what it does is it splits batches into micro batches, so it processes way faster than the normal methods when you are not splitting. So it's G5. Hoop is still leading. You have Lawless. This is true or false. Double points. So Oka serving engine achieves better throughput and latency by using batch level scheduling. This is true or false. So it uses something called iteration level scheduling. Yeah, that's covered in the last. Okay, now we have looper XX leading KLCH. This is the easy one, I guess. So which is true about onlines of flags? So it helps decrease HVM access, and the blue color one is like some random thing like you can. Yeah, it's a
Online software. All three. I thought it was online software.
Oh,
We can get it online.
my bad.
Compared to
I
offline.
mean, I meant like calculated software function online.
That's true.
Yeah. So yeah, still loop XX. Sorry for that. Again, true or false? It is hard to run inference on LLMs due to large memory footprint and low parallelizability. Is it true or false? Again, that was not a tricky one. Is just yes, due to low parallelizability. We have to have like large memory.
I thought LLMs were parallel, like they're able to be parallelized, but it's only like I agree with the memory part, but not the parallel part, because I thought the architecture of a transformer allows it to be parallel.
So maybe there should be some more nuance on the question, right?
Maybe it's training of inference.
I get
Yeah,
back on that.
training-
I
Training
put on
definitely
this
is
like
hard, but inference is also, something you can't really serialize. I mean, sure, the transformer is parallelizable, right? That's the whole point of going to a transformer rather than some sequence model like LSTM and RNN, right? Yep.
I put the source from source where I got that from on the slide. Yeah.
Yeah, sometimes our sources aren't that good either, so don't worry about it.
So this is a puzzle. So arrange the attention diagrams in order.
Be at the top.
You can drag it down. Yeah, so the first one is multi-head, then group query, then multi-query. Sorry, the image is smaller than I thought. Just looking okay.
Can you show the media so that we can see it lined up?
Show media.
Yeah.
It's like this.
Multi-head on top. Multi-query on the bottom and.
Group query in the center.
Yeah.
So we have the glory interplace. Actually goes to different place.
All right. Okay, so we're still going to present using this computer. Is that okay? Yeah, you can just run it from here.
To Mentimeter.
Okay, yeah, you can log in.
Let me do some setup first.
Yeah.
It is okay.
This one. You may want to not share your screen.
Exactly, yeah, I
Yeah,
saw it.
okay.
Oh, is the Zoom sharing it at the moment?
I think so, yeah.
Oh, that's annoying. Okay.
So you can stop share for a minute.
Pause share. Okay,
Yeah.
thanks. Cool. Okay, it works. Resume share and laptop. Okay, all yours. Thanks.
This is being shared on Zoom correctly. Cool. Okay. So today we're going to talk about data and knowledge. So we've already talked about how different amounts of data can help with scaling up and model size and all of that. Now we're going to talk a little bit more on the qualitative side, what goes actually build these data sets, and then we'll transition to the knowledge side, how that data is used. So first we'll go through a paper that's talking about how we document these absolutely massive data sets that are being used for training these models. We'll talk a little bit about some of the problems that can crop up in these data sets from how they're sourced, including machine-generated data. That's going to be a bigger and bigger problem, especially now. Data contamination from other benchmarks, bias and diversity problems in terms of toxicity, viewpoint, representation. We'll also talk about duplicate data and overall data ecosystems. And then the knowledge team will talk a bit about what knowledge bases are, knowledge encoding, and model editing. So how do we get models to use knowledge correctly? So first, the introduction to data. We all know how important data is. Models keep getting larger and larger in this now very outdated graph. That's exponential growth. Note the log scale for both the models and the data. It proves a point. It was a graphic I had. So we're dealing with data set sizes that are exponentially increasing. You can see at the bottom, we have, billions of tokens. What do we do with data sets that big? So historically, right, these were big data sets. We had the Penn Tree Bank, which is about 5 million tokens. This is a massive data set in the 90s. This was huge. It's mostly comprised of 2,499 Wall Street Journal articles. I love that one-off number. These were all annotated for parts of speech by people. And this was considered to be, a great resource. SNLI in 2015, the other example of a historical data set, was 570,000 human annotated pairs. And this was 2 orders of magnitude larger than other data sets of its type. But the important things to note here, as big as these data sets were, they were still all human annotated. They were intentionally curated from very specific sources and for specific tasks. And there was an emphasis on data quality. So like in the Penn Tree Bank, we wanted a lot of data, but we wanted it annotated correctly for person image. SNLI, we wanted it correctly annotated for entailment. Now, if we move to that post-2018-ish cutoff, these are the scales of data that we're working with. So like internally, Walmart generates 2.5 petabytes of data per hour. The Google search index is 100 petabytes. The Common Crawl data set was 320 terabytes as of April 2021. So I don't have the exact conversions between tokens and storage, but that's a lot bigger. So there was a paper that from, when was that, 2021, that described it, I think, fairly succinctly as unfathomable training data. We just can't fully comprehend how big this is. So in comparison, things to note about data now, it's scraped from many, many different sources, which is on the one hand, a great thing for data diversity. But on the other hand, can be really bad for data quality. So it's not annotated at all. Because there's so much data, we have to rely on filtering processes and automation most of the time. And the emphasis is on data quantity. Okay, so with that introduction to data sets in the large language model era, let's get into data documentation. So this will be based off of the Princeton course slides. We'll be looking at this paper, a case study on the colossal clean crawled corpus, which was a study that was done a couple of years ago at EMNLP. So what they look at is they look at the English split of C4. So C4 5 in 2019. It's a subset of the Common Crawl data set, which was made by taking the normal Common Crawl and filtering out any non-English text that was detected with Liang detect. Any documents that had like lorem ipsum filler in them, less than 5 sentences or words on a specific block list that the authors had curated. So these were like profanity, slurs, basically any kind of filters like that that you can think of. They came up with themselves. Once they had filtered out these documents, they also went through and tried to filter out any code, any lines that had less than 3 words in them, and any lines that didn't end with punctuation. So this isn't quite part of the current presentation, but we'll get to it a bit later. I want you to think about this filtering process and what advantages it has, but also what problems it could cause, or what are some potential things it misses or excludes when it shouldn't. After this filtering process, we were left with 365 million documents and about 156 billion tokens. And in total, it's 305 gigabytes, which is now still a small data set. But it is a very, very big data set if you want to go through and properly document it. So data set documentation for traditional offline data sets, especially if you're coming from an earlier field like computational linguistics, usually you're collecting data directly from participants instead of scraping it from online. Or even if you are scraping it, you have a strongly documented data source, you have a target source of data, you have participant information, you have statistics on your data, you have things that you want, and you have a specific annotation book for the guidelines that you're following on the labels in your data. Replicating this for scraped web data is very, very hard because we have posts that were made online that are just retrieved by computers. And now we have to figure out, okay, who wrote this? What is their native language? When did they write this? Were they the original source? All of this information that you have from something like a participant study, you don't have when you're scraping data. So we need to figure out a way to get some of that documentation back. And the obligatory, why do we care? The most overused XKCD comic in all of machine learning, quite possibly. We want our models to learn from diverse data because they're just working with data and doing. If we document our data correctly, it also allows researchers who work on data sets to improve data sets in the future. If they know what's missing from one, they can put it in a new one, they can test it. And it might also allow us to diagnose problems in models. If we see that a data set is missing data from a particular group, for example, and the model performs very badly for that group, that's a place to start in improving the data. So there are a few levels of documentation. There's the metadata level, which is looking at some of those first things I mentioned, like where the data is from, who said it, when they said it. There's also the included data level and the excluded data level, which we'll get to a little bit later. But for now, let's look at metadata. So the authors in this paper look at 3 specific questions for metadata. They want to know who wrote our text in terms of kind of capturing native language was the goal with this, and location. So they measure this with geolocation. They want to know where the text was collected from. So they measure the site domains that are common in C4 and site names that are common. They also want to know when the text was written. So they look at when the site was archived on the Internet Archive. So what they find is that for geolocation, so first of all, they use web page hosting location as a proxy for posting location, which is not great. It's not perfect, but it will give at least some idea of where some of this different data is coming from. So they find that the vast majority of data in C4 comes from the US. And second to that is unable to disambiguate, which, again, not so surprising because of the metric that they're using. But the most important thing about what we see here is that the amount of data per country isn't representative of the English-speaking population. So where is it? This one was fun. Singapore is here. Singapore is fairly well represented in C4, relatively speaking. China, though the main language is not English, has far more English speakers than Singapore, just because of the size of its population. China is less well represented than Singapore in C4 English. India, as another example, is below Germany. If you compare this to the list of countries ordered by English speakers, this does not match at all. So this is already a potential problem. Next, they look at the site domains that are common in C4. So they do this by tokenizing the website names using the Spacey tokenizer and looking at what the top 25 most common suffixes are. So they find that the popular domains that you'd expect, .com, .org, .net, all of those are very common. But they also find some country-specific domains, even for countries with languages, primary languages other than English. So you can see, like, here is a suffix for Russia. And another thing they find is not quite making the top 25, but some other common suffixes are military or defense specific suffixes for the US and the UK. So in terms of top 25 domains for data sources, that tells us some interesting things about what's contained in this data set, potentially. Then they go on to look at specific websites. So they just measure the full site name. So what they find is that the most common source of tokens in this data set is patents.google.com. And also slightly lower on the list is just patents.com. So patents and legal documents are very, very prevalent in this data set. So is news. You see a lot of news websites throughout here. General information like Wikipedia, some science sites. Travel is also fairly well represented. And okay, I have a question on this one because I want to make it more interactive. So What do you notice that's less represented that you would
EDU's
expect
domain.
to be?
EDU's domain.
EDU's domain.
Yeah.
Yeah, like education sites. Okay, yeah, I mean, we would expect that. We work with that all day.
Medical data.
Medical data, there's a little bit of medical.
Huh.
There's like NCBI. But yeah, maybe
Oh, this is just like the number of pages, right?
it's by the number of tokens. Yeah.
As in like the amount of content that they put online.
Yeah.
Other people? Anyone else want to weigh in on Hannah's questions?
Why is Wikipedia and M.Wikipedia separate?
Oh, because one is the English mobile version.
Yeah, but as in they contain the same content, right?
They contain the same content, but they would be scraped differently. So it's measured based on the entries in the data set, and they would be.
In the cleaning process, they probably should have removed like the mobile version.
Yeah, so that's another point that I think, do you cover that? Who covers that?
Not on this one, yeah.
Yeah,
But it seems deduplication is the other. Yeah.
yeah. Yeah, so what Nick is pointing out is that both Wikipedia shows up twice. English Wikipedia shows up as the second entry, but then the mobile version of English Wikipedia shows up right under it. And in theory, those should contain exactly the same entries, which means that there's probably a good amount of duplicate data in the data set, which will cause problems that we'll talk about later. The third thing that they measure is the date of posting information. So they measure this using the Internet Archive first index date, which is again not the best way of measuring it, but you work with what you've got. So what they find is that 92% of the data was written in the last decade, so between 2011 and 2021. But it is a very long-tailed distribution. So there is a significant amount of data that was written before that as well. It's just not to the same scale as what was written in the last decade. There's also the problem that about 45% of the sites in C4 were never indexed. So those we can't say much about. Okay, on to the second point, which is what could be included in our data set, good and bad. So I'll talk a little bit about data contamination, which is when benchmarks wind up in training data, and machine or human authored, which is looking at, well, who wrote the data. This can be pretty hard to talk about. So for machine generated data, we're going to go back to this site prevalence plot. So some of the most represented sites are for patents. And something about patents is that records exist for very, very old patents. And the old ones exist in digital form thanks to optical character recognition. So they've been scanned in and processed using other machine learning models. The problem gets worse because patents from other countries or non-English speaking countries are commonly required to be in that country's primary language. Google patents machine translates those so that they can host them in English online. So those are two sources where that text was not written by a human necessarily. So they provide this example, this is from the Princeton slides, but they provide this example of why this could be a problem. Looking at earlier examples of machine translation, you have examples like this, where this is the original PDF. And then the machine translated version of it is A, complete gibberish, and B, is not well aligned at all. with what the original is saying. So we don't want our models to be trained on this data because it's just garbage. It won't be useful. So it's important to know when there are instances like that in our data sets and ideally try to filter them out.
Check.
No, I'm just on the wrong. There we go.
Yeah.
So they tried to measure how big of a problem the machine translation was specifically. They went through the patent documents and they split them by country of origin and the language that they would be in. So they found that about 17,000 of the patents, or 20% of them, were most likely machine translated. The other 80% were English, but there's an amount that they can't quite quantify that probably used OCR. They can't quite quantify it because it's A, not documented, and B, it's kind of hard to go back and find. You can do it for specific cases by searching for like something very old that you know was patented a while ago, and it'll show up twice in the data. But it's very hard to actually quantify how big of a problem that is. The other part that they looked at was data contamination. So, motivating example for data contamination. I don't know if anyone saw this on. So there was this, it was inspired by something else, but we have this example here. This model obtaining, 100% scores on these very hard data sets. In the new paper, pre-training on the test set is all you need.
It's a joke. It's a joke.
Which is a joke. To clarify, it's a joke. Don't do this. Data contamination is the percent of a benchmark or test data that is in your training data. And you can also think of it as the amount of performance that you can get for free. So if you have 100% data contamination, of course you're going to get 100% performance with a largish model. This is a big problem for data sets. We open source data sets a lot because science. We like to provide things that other people can build on. But another problem is these data sets now are also usually built from scraped data. So if you have something like the CNN Daily Mail corpus for summarization, which is scraped from these news sites, something trained on Common Crawl has probably also seen that data. There are two types of contamination that they look at. There's input-only contamination, which is only the training data is in the training data set, no labels. And there's input and label contamination, where you have everything, inputs, labels, your model has seen it all. And what they find is for input and label contamination, so first of all, there are significant amounts that they find for all of the data sets they look at. Some of these numbers are pretty small, like for the TIFU Reddit data set. It's only 1.87% that they find exact matches for the label. So that's like, it's split into a prompt and an output. They perform exact matching over the text. But when you consider the performance improvements that papers advertise for new methods, being so small, if you have 1.87% of this data set in the training data, that's 1.87 performance that you can just get for free without actually improving your method. So these numbers are all significant. They're all bad. But data sets with single sentence outputs highlighted in orange do tend to get higher exact match rates. So it does tend to be a problem for shorter data more than long form data. For input-only contamination, first I want to address why this is a problem, because this is slightly different from the usual training on the test set case. It's a problem because a lot of these data sets are also used to measure few or zero shot performance, where in theory, you've given a model no examples or only a few examples of training data. But if it's actually secretly seen 1,000 examples in the training data, that's not a fair comparison. So there are really, really variable amounts of input contamination found in C4, ranging from 53% to 1.8%. But this was, again, a problem for all of the data sets that they tested on, and these are all very common evaluation data sets. So with that, we'll go to Nick for the next portion of
Okay, so I'll talk about bias and diversity. There'll be some audience interaction also, hopefully. Okay, so just prepare your phones or something, I guess. All right, so what is diversity? Just want to, before we start, it's always important to define your variables, initialize it. So diversity, we're going to talk about two kinds of diversity, just to make sure that we don't get mixed up. We're going to talk about diversity of representation. So that means, do we have people or data that is not in the data set for whatever reason? And then we're also going to talk about the diversity of data types. For example, earlier we saw quality of data set, right? So that's where the data type comes in. So just to kick it off, could you join this Menti? How does this work? I am so bad at using a Mac. There we go. Okay. Okay. Let's see if we can access Menti and 976932275. I'm going to assume everyone here has used the dataset at some point of time.
Can you explain the questions a bit more?
Right, okay. Yeah, so basically the question that I'm asking the Menti is asking whether you have personally done dataset scraping and or whether you have used models that use datasets. And then for these datasets, how big is the dataset and how often do you use it? So I just want to get an idea of are you guys generally using bigger data sets, smaller data sets, and how often do you tend to use it?
What's the unit?
Yeah.
Subjective opinion. Like, do you feel it's a big data set? I mean, if you can finish your training pretty fast without your GPU crashing, then I would say that it's reasonably small. If your data set can't pick your GPU and you need to do a lot of tricks, then it's pretty large. Okay, so I see that there is a lot of averages taking place, but I'm getting the general vibe. You guys feel that you're not using very big data sets and you are not using them that often. So not using them that often is fine, I guess. And not using big data set. Okay, so later we'll be talking about the size of data set, and we'll find that the size of data set actually has an effect on the quality of the data, not just because of the quantity, but because of what is included in it. So let's see. Yeah, so we also think about this. If let's say we use the data set and the data set has bias, what will happen to your model? I mean, so can elaborate what kind of bias might you expect to see? Yeah, just type it in, then it can appear. And I want to try a trick because now apparently Menti has automatic AI topic clustering. So I want to see whether that works. Okay, so if you look at this, I see a biased model will exhibit bias. That really feels like a machine learning model, right? You have the training data that says bias. And then the machine learning model is coming, there will be bias. Input is output. Not politically correct because you only output. Okay. So this is more or less correct, yes. That basically your data, whatever you put into your data set will be an output that you get. Yeah, okay. So it does feel that what you guys are telling me is what I asked in the question. Okay, I like this. It won't be representative of the truth. But that's a very good question, right? So what is the truth, right? So is your data set the truth? Does your data set represent the truth? Deep poor performance, yes. So when we talk about real world usage, then you are talking about generalizability, right? So then what you're saying is that your data set does not contain enough to represent the so-called truth, whatever the truth is. So I think these two are similar ideas, and I think that links to the weakened ability. Okay, cool. So let's get back to the presentation. Just pop this. Oh, man, I have no idea how to use a Mac. Yeah. Okay, so I think you know a lot of stuff has happened with this guy called Elon. Don't know if you know him, but yeah, there was some messiness earlier this year and last year, and apparently he removed the ethical AI team from his company, and that caused a bit of a kerfluffle. So you can go read out on it, but I was quite shocked when that happened because honestly, when you talk about AI, I think more and more nowadays people are starting to realize that we need to start thinking about ethics. A lot of bad things can happen if we don't do that. But not only that, as you guys alluded to in the quick survey just now, if your data is shit, your model is shit. So even if you don't care about ethics, which you should, by the way, you don't care about ethics, but even if you don't care, you should care about your model performance. So there are some studies that actually carefully tried to parse out the effect of this. There's this paper that came out in our sources where they tried to find the biases. So it set up the large language model and it prompted it with certain keywords. For example, if you see the highlights here, Asian, Caucasian, who was a bad driver? So they have it's the same gender, but different race. And then they wanted to see, does the large language model is it racist? Is it sexist? And so on. So building on that, another paper then automated it. I think the first paper, they manually came up with the prompts. This other paper then developed a system to automatically generate these prompts. And then they ran it on the C4 dataset. And guess what? To no one's surprise, there is bias. So these are some earlier studies. This year, there was a very interesting study. So that study was more abstract, more general. They were just asking questions about a large language model. For this study, they took the context of theater scripts. They got a chinchilla-based model. So first was chinchilla, and then after that, they went to there's a typo, GPT-3, sorry, yeah. They used chinchilla first, and then they asked chinchilla to write theater scripts. And then, depending on the names that they provided for the characters, they started getting racist results. And then there's another issue with scripts in general where you find that it's very male-dominated. Main characters are always male. And as expected, the script writing model had that issue. So we have talked about these biases. We have talked about if you have bias in your data, then you expect your model to be biased. But where do these biases come from? So I'm just going to try to ask you guys for some
There we go.
All right, sorry about that. Okay, so you guys mentioned that the source of data itself is problematic. But one thing that I didn't see in your responses is that actually it's not just that people are problematic, but we are only looking at certain types of problematic people. Or rather, we're only looking at certain type of people. So the thing about online data is that it's usually scraped from very Eurocentric, I guess that's one word for it. If you think about it, there is an underrepresentation of things that are not English on the internet. And specifically, as with most places in this world, the data sets are dominated by heterosexual white men. So someone talked about the patriarchy earlier. Yeah, that's more or less it. So language, gender, and age group, there are biases in the data, and it depends on where you get it from. If you get it from GPT, if you get it from Reddit, if you get it from Wikipedia, you'll find certain trends in the data. So there are some studies that looked at it, and then they find that if you are European, you are white, you are straight, you are Christian, you probably are more represented in the data set. If you are, well, if you are a minority, you are a minority in the data set. So that is quite unfortunate because it means that when we train models on the data, it's more likely to represent people who are already represented. But so just now I said that if you are English, or rather if you communicate in the English language, then you are more likely to be represented on the internet. But actually, it also depends on the kind of English. So if you type in very formal standard English, you are represented in a data set. If you use non-standard English, you are not going to be represented much in the data set. Interestingly, this is not just about language. You also have differences in political opinion. So this study, they compared large language model trained on some feedback data sets on things like appropriate behavior and ethics, and then they compared it to the Pew Global Survey. They found that if they don't do prompting, the data set output, which is represented by the pie chart on the left, is more similar to the human participants from USA. But in fact, the other finding that they got was that it's extremely extreme, the model, and actual humans are more diverse. Now, what's interesting is, if they then prompted the large language model by saying, how would a person from this country, or even better, they change the language of the prompt, they were able to get the responses to be more similar to people from other countries. So it's quite fascinating. And then, depending on the training data, you get different political opinions. And what's really fascinating is that the data before and after Trump shows different political opinions. So also, BERT is more conservative than GPT because they use older data, which is quite interesting. And this is the part that I talked about earlier, model size. It seems that when they release different model sizes, the subset of data represented in the model, actually it becomes skewed. So maybe this needs to be paid more attention to. So yeah, there are issues, and you really should consider carefully what data set you are using when you do these studies. Okay, I'm going to skip this one. I'll just go straight to it. Earlier on, Hannah talked about how the C4 data set has some censorship. So it tries to remove certain problematic words. And for what I understand, it uses the same block list as Shutterstock. So just to let you know, there are some vulgarities here. But what this slide is trying to say is that there are a lot of false positives. And I'm sure you know that if you ever tried moderating a forum or online gaming or whatever, you know that trying to remove vulgarities is really difficult because it's different in every language. And if you just try to do like, for example, regex filter or whatever, you will get a lot of errors. So you could possibly do a study on how to remove vulgarities from text and correctly identify it. Yeah, so that's the thing. Their method was that if there is a bad word in a document, they remove the entire document. And this may be a bit of an issue, like should you just remove the entire document or should you just remove the individual words? There I'm not sure about it. You can think about it, and I'm just going to move on first because I realized there's not a lot of time, but basically there was a finding that if you look at the data set, people, as you have said earlier, people are terrible. And so minorities tend, in the data, text with minorities mentioned also tend to be more negative in general. But also, as a result, their discussion then gets filtered out in the data set. Who are already getting bullied online are also, because of this bullying, therefore not represented in the data set, which is a major issue. So then the other thing is that if you upload a data set has details about people that will then put them in danger. So this is something very important to consider when you're scraping your data. Just because it's online and you can take it doesn't mean that you should make it more available to everyone. Like, what if your large language model then puts out data that will harm people? So you have to be careful about that, especially things like safety and medical records. So we talked about representation. We're going to talk about data types. So there is the PAL, which there's a link to the PAL inside the Slack group now. The PAL, instead of just taking everything from the internet and putting it together, they carefully put together sources that are considered more high quality. So of course, that means more work, but supposedly it gets better results. So this is a rundown of where the data comes from. You can see that a lot of it comes from things like PubMed, from Archive, from Stack Exchange, and everyone knows Stack Exchange is the best place to get answers from. So they tried doing different things compared to GPT-3. And
back one slide.
sorry?
Can you go back one slide?
Yeah.
So there's a green box next to your 825 that says pile. So what is that?
Why is it recursive?
Yeah.
I think it's like an earlier and a smaller version of it.
Oh,
Something like adds on to it. Yeah.
I see.
By the way, I think it was blocked by the bar just now, but blue is academic sources, green is from the internet in general. Yeah, so you can just see from the top. Yeah, so anyway, they compared it to GPT-3 and they found that in the majority of tasks, the PAL actually did better. It's just a few small tasks that PAL did not do as well. And this is of note. Okay, by the way, I forgot to mention, they compared to GPT-3 using GPT-2 trained on PAL. So even though GPT-2 has fewer parameters, it still outperforms. So what they're trying to say is that quality is better than quantity. So, but the thing is that the task that they use, I guess you can say that the stuff that they were testing it on is stuff that this quality data set is more suited for. So what if you want to do other tasks? So what I'm just trying to say is that when you plan how to do your research, don't just take some data set that the internet says is high quality and assume it's high quality, because even if it's high quality, if it doesn't match the task that you want to do, then there's no point doing that. So in conclusion, what I want to say is, don't blindly follow what you see on the internet or what other people say. Think about what you want to do. Run some analytics, visualize your data before deciding what you want to do on the data. Think about whether or not you want to filter the data, whether the filters are correct or useful, and then try to understand your data. So there's some work that tries to document it, like data statements, which basically describes what the data set is about, model cards, which describe the model, and so on. Well, everyone knows documentation is important. That's why you put comment text on all your code, right? You all do, right? Yeah. Okay, then we'll go to deduplication, where our colleague is unable to make it today, so he has prepared this presentation.
Hello everyone, I'm Yixi. Discussing is data deduplication and data ecosystems. Let's start with data deduplication. I will be giving an introduction based on this paper. Deduplicating training data makes language models better. The first question is, why is deduplication necessary? The paper found that existing language modeling datasets contain many near duplicate examples and long repetitive substrings. These duplicated data encourage models to memorize, thus reducing their generalization ability. Taking the C4 dataset as an example, we can observe that in these two text segments, only a few words differ, like Canada, USA, May, April, while the majority of the content is entirely duplicated. This is what we refer to as near duplicates, and long repetitive substrings are easier to comprehend. They are essentially very long strings that repeat throughout the dataset. The most frequently repeated substring in the C4 dataset appears more than 40,000 times. In response to these two scenarios, this paper introduces two deduplication methods. First, to address long repetitive substrings, the authors propose exact substring. If two examples A and B share a substring of at least 50 tokens, then the substring is removed from either A or B. This method matches exact substrings, which is relatively straightforward to understand. Regarding near duplicates, the authors primarily determine duplication by calculating the similarity between two documents. Specifically, if two documents are matched by the main hash algorithm and their added similarity is greater than 0.8, they are identified as duplicates. And main hash is an approximate matching algorithm widely used in large-scale deduplication tasks. The main idea is to use hash functions to approximate the Jaccard index, which is a statistic used for gauging the similarity and diversity of sample sets. The Jaccard index is defined as the size of the intersection divided by the size of the union of the sample sets. To be specific, given two documents, Xi and Xj, let Di and Dj be the set of n-grams of Xi and Xj respectively. If the Jaccard index between Di and Dj is sufficiently high, it is likely that documents are proximate matches of each other. Then, how to decide Di and Dj? Main hash constructs document signatures by sorting each of the n-grams via a hash function, and then keeping only the k-smallest hashed n-grams. After obtaining the Jaccard index, the probability that two documents are considered a potential match is calculated using the following formula. In this paper, a probability greater than 0.8 is considered to indicate duplication between the two documents. In addition, this paper also calculates added similarity, where added distance is the minimum number of operations required to transform one string into the other. For more detailed definition, you may refer to Wikipedia explanation. Due to time constraints, I just provided a conceptual explanation of these methods here, and you may find the implementation details in the original paper. Then it comes to experimental results. These results indicate that deduplicating the training set using these methods can be beneficial for training. On one hand, deduplication significantly reduces the rate of memorizing training data by the model. And on the other hand, training models or deduplicated datasets is more efficient. Additionally, deduplicating training data does not hurt perplexity. All of these findings emphasize the importance of deduplication. Therefore, paying attention to the quality of data is essential. And so far, we have mostly focused on the analysis of existing data sets for large language models, as well as documentation. But data is a broad concept which can be studied from many other angles. For example, data management and in machine learning research, we tend to think of data sets as fixed objects that you collect and you feed into a training algorithm. But in the databases community, there is whole subfield thinking about the ecosystem in which data comes to be and is used. And this is particularly relevant in industry. So why is it necessary to pay attention to the data ecosystem for us? One significant reason, using GPT-3 as an example, is that the resources necessary to create the best performing models are found mainly in the hands of big technology giants. While GPT-3 shows interesting behavior from a research point of view, such models are private and not accessible to many academic organizations. The current situation promotes a duplication of energy requirements and the environmental costs due to the duplicated training of large models in private settings. Moreover, even when accessible, these tools have not been designed as research artifacts and, for instance, lack access to the training dataset or checkpoints, which makes it impossible to answer many important research questions around these models. Finally, there are shortcomings in the text corpora used to train these models, ranging from non-representativeness of populations to a predominance of potentially harmful stereotypes or the inclusion of personally identifying information. The Big Science project serves as an excellent example of data management. To address above issues, they are developing a framework for responsibly curating quality data sources. Here is a visualization of their framework. The first step to devise a global data management structure is identifying specific roles in data governance here from right to left. They have the data rights holders that can have either commercial ownership or personal rights over the data. They have the data that typically manage and create the text, and the data steward that oversees the general flow of data and its uses. Then they have the data modelers as NLP researchers who conduct statistical analysis and train models on the aggregated text data. And another category is data helpers that includes lawyers, advocates, and anyone else who can help provide tools and the context to help with data governance. You may check the link for more information about this project. Another concept is data dignity, which is originated out of Microsoft and radical change that seeks to think about the nature of data. Some key points are shown in this slide. I think that these concepts emphasize the relationship between data producers, which could be anyone, and data users. In current situations, as data producers, we often do not know how our data will be used. We can benefit from the data being used. Many companies, at least, have derived significant value from it. This represents an imbalance. For example, it's well known that personal data privacy is challenging to protect now. However, these are just some of my personal thoughts. and I must say that I do not have an in-depth understanding of the concept of data dignity, so these thoughts may not necessarily be accurate. You may explore the related readings listed to consider these issues from a more objective perspective. Anyway, now that we understand the importance of the data ecosystem, creating a better ecosystem may require consideration of various aspects. I believe that, even at present, there may not be a perfect solution. Data belongs to groups rather than individuals, and the data ecosystem should be improved through collective efforts from groups. In comparison to explanation, this topic requires more of a discussion. Perhaps everyone can think about it. What should the ecosystem where data is created and used look like? And what's the best practices for creating data to maintain quality and security?
Can you just check the chat?
Okay, let's see what's in the chat.
Oh,
That's the old messages from earlier.
alright.
Yeah.
Close that.
Okay, so who was next?
So let's first give a applause for our presenter.
Next. Okay, cool. Yeah, you go ahead and run, then the person who is not here.
Mhm.
Yeah.
This one.
Yeah, the second presenter for your section, you need. I realize you might want to run from.
Where's the present?
Yeah, it's hidden. I'm scared to close this. I don't know how Macs work.
Let me clean up the windows.
If I close this word, okay, it's fine. Yeah.
You can close the chat one too.
Okay. Sure.
Close the chat.
Close the chat. I can close this, right?
Yeah. And you can just anchor this back to the top by pressing that. This way.
This?
Yep. Yeah, get out of the way. And you can shrink this to the smaller one.
Yeah.
Yeah. That's
Okay.
good.
All right, so today I'll be presenting on knowledge bases. So before I begin, we should cover what exactly is knowledge base.
I just had to press somewhere on the slide. It's, yeah, finish it.
Okay. Oh, how do I go back? The arrow keys, right?
Yeah.
Okay, yeah. So what are knowledge bases? So before we thought of like LLMs, and you can ask ChatGPT or some knowledge that you want to know about. Before this, people built knowledge graphs in this manner. So we have two objects. We have the object relation and the subject relation and the object. So they are all like entities inside the graph. And how you link up objects with subjects is through a relation. So basically you have a lot of this kind of different knowledge graphs, and these knowledge graphs form up a knowledge base. So in this case, for example, we have subject Edward Hopper, who is related with a relation of citizen of to United States. So with this knowledge base, another example would be this one, Atomic, created in 2019. Right. So with this knowledge base, people can write queries to get information out of knowledge bases. And we can use this for a lot of different applications. Like for example, with like Alexa, you can ask Alexa something, and then Alexa will probably interact with a knowledge base to give you what you want to know about. Right. So the issue with this is that building a knowledge base is very troublesome. So for example, suppose you want to build a knowledge base about, I don't know, Edward Hopper. You have to get a bunch of text, like Wikipedia text and stuff like that, and then put it through a pipeline. This pipeline involves data processing, entity extraction, relation extraction, and ontology extraction. And it's quite troublesome. So, for example, so you see, another issue is that knowledge bases rely on a lot of fixed schemas. Populating the knowledge base is very complicated. And lastly, your pipeline might have a lot of issues, and information extracted might have a lot of errors. So you can use a language model for knowledge bases as it's pre-trained with huge corpus of data. You don't need any supervision during the training. And it's very flexible with how you can query the language model. Like, for example, with language models, you can just ask it in natural language and it's usable off the shelf. Now we're gonna ask the question, how can we ensure that language models store knowledge? So to answer this question, there's this paper in I think it was 2020 or around 2020, that was trying to answer this exact question. How can we ensure that language models know something rather than just trying to tell you, I don't know. And so this paper, they created this thing called the Llama probe. It stands for Language Model Analysis Probe. And what it tries to do is try to evaluate whether a language model knows factual and common sense knowledge. So what it does is it collects knowledge sources from multiple sources from different data sets and tests whether the model knows a fact about a particular knowledge source. So to do this, they define there's a couple of definitions. So for example, a fact is defined as a triple, like as shown in the knowledge graph, it's a subject followed by relation and an object. And then a language model knows a fact if it can predict a close sentence. So previously over here, we have the triple, and to query the language model, it asks the language model this sentence and ask it to predict what's the word in the blank. And if you can do that, knows that fact. So how does Llama evaluate whether a language model knows a fact? Through you take the sentence with the clause, you put it through the language model, and the language model will try to predict the masked word. And then we use mean precision at K, and if its answer is in the top K positions, then we assume that the language model knows the word. If not, then we assume it doesn't. So for this paper, they use 4 different models: BERT, Elmo, Transformer XL, and Ferris sequence fconf. So these are the data sets that the models were trained on. So for Ferris sequence and Transformer, we use Wikitext, and then Elmo, it's on Google Billion Word and Wikipedia, and BERT's trained on Wikipedia and book corpus. Next, how does Llama ensure that the LMs are all tested fairly? We use number one, we ensure that the output generated by the language model is unified. So each of the language models produced can only predict are made to predict only a certain vocabulary of words. And then next we try to get the language model to predict the word using how it was trained on. For example, with BERT, it's trained on, for example, for some of the models that are bidirectional, you test it to see if it predicts one way, and then test it to see if it goes the other way also. Then we use that result for figuring out whether it knows something or not. So for the knowledge sources that we tested on Google RE, which is 6,000 facts manually extracted. And then using the facts, they got people to manually build a natural language sentence for the language model to test the language model. Same goes for T-Rex, which is a subset of the Wikidata knowledge-based triples. And they also manually got someone to write out a sentence for the language model to predict. And ConceptNet. ConceptNet and Squad. So they're all just data sets to test them. Now, how can we ensure that? So why do we compare these language models? Why do we compare the results of the language models with? So they use a couple of baselines. One of them is base frequency. So for this baseline, we try to rank how frequently an object appears given a certain relation. So for example, here if you have cats, English phones, so over here, suppose we have a relation and this relation has these objects that it points to. So over here for this particular relation, we assume that this relation will always point to cats because cats appears the most frequently. Then we have this model by Sorokin and Gurevich, the relation extraction model. So it extracts relation triples from sentences, and then it trains on the sentences that express test facts. Sentences that express test facts. Okay, I'm sorry, Okay, so for this model, they use two different types of models. There's the standard one which uses the string matching to link entities together, and then the second one is use an oracle. So the oracle sort of like I'm so sorry, I forgot what I wrote.
Okay, do we have the paper that
Yeah.
you're talking about?
Yeah.
The Dr. QA?
The paper is linked.
No, that's the other paper. That's the language model is knowledge bases, but you're talking about
This one.
paper, the Sorokin and that paper.
Yeah.
Which one? Because Serena has written a lot of papers. The second author is the current president of ACL, so that's why. Yeah, so I just want to know which paper it is. Is it the 2017 paper?
This one I'm not sure. I gotta go check the paper.
We're gonna put it on Slack, so if you guys want to take a look.
The last baseline that they're using is the ERQA. So in terms of how you evaluate these baselines and the models, same thing, they see how much correct results you can get per relation. So a limitation with this paper, the llama method, is that number one, all the templates were defined manually. Next, all the queries made were all for single tokens for the language models. So the language models do not predict multiple, for example, cannot predict a multiple closed sentences. And lastly, the language model only predicts the object slots. So for example, Cairo is the capital of Egypt. The language model can only predict the Egypt type, not the subject or the relation. So here we have the results. So here we can see BERT performs best for the entirety of Google RE, except for the birth date one. And it performs quite well compared to the baselines also. And BERT also performs the best for the T-Rex dataset when there's only one word answer, but it doesn't do well for the multiple objects to one subject relation. And over here you can see that out of all the language models, BERT also far exceeds all of them. So in terms of the conclusion that we can derive from this paper, is that number one, BERT performs best out of all the language models, and that it is competitive enough compared to a standard knowledge base that is trained on the best data with an oracle. Okay, right, that's it. Thank you.
Yeah, or like the fake verification part for like llama, right? Because I thought there were like other data sets there or other benchmarks that also do this kind of fake verification like fever. So like, is there an advantage of using llama over these like benchmarks?
Sorry, I'm not very clear. I don't know much about, yeah.
Yeah, it's okay. But because like I thought there's other benchmarks. So like, what's the purpose of llama? Like what kind of advantages does it?
When was fever released?
I think it's quite an old benchmark. We check.
Well, just to be clear, this is llama with one L and not
Yeah,
two.
one L.
The older paper.
And this paper was created by
2018.
Oh.
2019, yeah, this Llama paper. Yeah, Warren, you were asking about what?
About like this other benchmark that also there's like effect verification, like fever and things. So like
Yeah.
what's like the advantage of using Llama over these other benchmarks for verifying effects in health?
So they're introducing a probe, right, which
Yeah.
is a bunch of different sets of knowledge sources with sets of facts. So fever is a data set that's specifically looking at fact verification. Yeah, so I think they're looking at different types of problems, not exactly the same, like, yeah, but it's a good question. So the people who are working on fact verification, they tend to use the fever data set. They don't refer to Llama, this particular paper very much, because this is more about using, looking at whether language models can encode the same facts as knowledge-based ones, right? So it's not necessarily about how do you deal with inconsistencies or contradictions in data sets. Yeah.
Thank you.
Yeah. So one of the presenters, one of the paper authors was here last week. So language models as knowledge bases. Patrick Lewis, he was at the Lambda workshop last week. So he's if you have questions, you could ask him or we can ask him about it. Okay, and now our
Now we have the next
presenter is
presenter on.
around. So especially if there's anyone on Zoom, just make sure that they can hear it. If you're on Zoom and you can hear our microphone, but you may not be able to hear the text.
Yes.
Let us know.
Hi, I'm Liangtao, and today I'm going to introduce knowledge encoding models in this part. First, what is knowledge encoding? So let's see this picture.
It's good.
Stop playing through the speakers.
Yeah.
If we set it up.
How did you guys do it last time?
Coding, we can
Yeah, I think that's the difference. Like, of the presentation was about like the triplets, because like you have a triplet form, then you can draw the links and stuff. Oh, this is like more of the links instead of just the fact itself. Yeah, definition of the fact is the triplet. Oh, yes. And then there are a bunch of algorithms out there that can use these graphs to kind of. Oh, so the data from the triplets and you know like only larger and larger graphs. Yeah, I guess what that's how Alright, so it's like more of like getting the facts from the knowledge graph versus like just a single discrete fact, which is what I'm doing. The definition, yeah, because fever when they say facts, at least like on the brief class, it looks like the fact that in plain English, the fact is that's a fact. But this Llama, this one is more for like knowledge graphs where there's like a relationship.
Yeah, like so this paper is specifically, it defines a fact as something that a knowledge graph has, which is a subject, the subject relation object thing. So it wants to test whether a language model has that representation inside it, right? Yeah. So then to do that, then it creates then they get people to create a closed natural language sentence, and then they just ask the language model to fill in the blank. Then if it can fill in the blank, that means it knows a subject relation object, right? Yeah.
All right, that makes sense. Thanks.
Yeah, so I think we're exactly right about that, right? When we're talking about a knowledge graph, it has triples, right? And the idea is to be able to recreate that knowledge graph from queries, right? Whereas fact verification is specifically about asking a question and seeing whether it's true or not based on data. Okay, so let's thank our presenter first. And we'll continue playing the video. Let's just double check that it's fully on.
Coding, we can assume that for some of the nerves in language model can store the knowledge in the hidden layers like this. So is this knowledge really stored in these nerves, and how is it stored? Papers, how much knowledge can you pack into the parameters of a language model? First, we know that to solve open domain QA, there are two approaches to do it. First is called open book QA, which use questions and actual results
Was it
are
playing
given to the
last time?
models. So the models can use the knowledge from the actual results to solve the questions. Another one is closed book QA, which the model only have the questions and they should learn the knowledge from the Python. So in this paper, this one measures transfer learning performance or knowledge on question answer tasks with a closed book approach. They just use T5 model to do fine-tuning in QA. And let's see some experimental setup. First, they use 3 QA data sets, natural questions, web questions, and trivial QAs, which are not used for pre-training T5, which means that T5 didn't know this knowledge. And they use 4 types of model size from the base to 11 billions. What's more, they use additional pre-training tricks, the salient spank masking, which was proposed in this paper. And we can see the results. Above is the SOTA retrieval-based methods, which is open book results, and this is the results from this paper. We can see that when the scale is become large, the performance become better, and the SSM method seems improve the performance. And we can see that when we just use the largest model size of T5, we can get equal book. So it means that with the largest model size, it can store more knowledge. So how does the language model pack this knowledge into the parameters? The second paper I introduced today is knowledge narrows in pre-trained transformers. In this paper, it proposes a concept of knowledge narrows. So first, let's recombat some backgrounds of transformers. We are familiar with these formulations of transformers, and as we can see, compared to the equation 2 and equation 3, we noted that the formula of FFN, which is feed-forward network, is quite similar to the self-attentions. It's just different between the activations methods. So let's think we can see 2 of the FFN's layers as the key values layers, and this narrows in the hidden layers is as the knowledge narrows. So we can build FFNs in transformer as key value memories, the same as the self-attention. So let's do some experiments to verify it. First is knowledge size attacks. In this paper, it implied the fielding black closing task to assess whether a pre-trained model knows a fact. As we can see it with these HRT tuples, where H and T are the 2 entities and the R is the relation of these 2 entities. And we can build these prompts to let the language model to predict the 12 entities. If the model can knows the facts, so it can predict the correct answer, right? So this paper, it proposed a way to calculate the attribution scores of knowledge narrows. So in this formulation, they gradually change the weight L from 0 to its original weight to calculate by the pre-trained models, and meanwhile they just do the integrate the gradients. We can see that this part just calculate the gradients of the model output, which regard to the WIL. And then as alpha change from 0 to 1 by integrating the gradients, this attribute scores calculate the output probability change caused by the change of the WIL. So if the network has a great influence on the expression of a fat, the gradient will be salient, right? So which in turn has a large integration values. But directly calculate the continuous integrand is intractable. So they just instead of use the Riemann approximations like this way. So in order to identify knowledge narrows more accurately, they propose a refining strategy, which is aimed to fill out the 4 positive narrows in one times calculate. So they just use multiple diverse prompts and with a refined strategy to retain only narrows that are widely shared among these prompts. Here is an example of the template, the multiple prompts for relations, which is in this dataset. So let's see the whole pipelines to identify knowledge narrows. First, we given a relation fat HRT. So first, just produce n diverse prompts. And second, calculate the knowledge attribution scores of narrows with measurables. And then to retain the narrows with the attribution scores which is greater than the threshold t. Finally, just use the refine strategy to refine the knowledge narrows shared by more than p pentagram percentage prompts. So let's see the experiments in these papers. In this paper, they just use birds and as the base models and use this parallel data set built by the experts and commutate various prompt terms for relations from a data set. And we can see these visual figures. You can see that most fat-related narrows are distributed in the topmost layers of the pre-trained transformers, which means that the fat knowledge seems to be stored in the higher layers. And let's see these tables. In the baseline, they just use the outputs of the model as the attribution scores, and this is their method to calculate the attribution scores. And we can see that with these knowledge narrows, in their methods, they can see that different fats was stored in different narrow things. And then they just do some experiments about knowledge narrows affect knowledge expressions. First, they just do suppressings. They just set their narrows activations to yellow, and they found that the suppressing knowledge narrows identified by their knowledge attribution methods leads to a decrease about 29% on average. And then they just do amplifyings. They just double their knowledge narrows activations, and you can see that the correct probability is increased by 31% on average. What's more, they just do some case studies. One of them is updating fats. They want to change these tuples to another tuples, which just change one of the entities of it. So what they do is, first they identify the knowledge narrows of HRT, and then they just retain the knowledge narrows that are shared by less than 10% of intergeneration fats. They just get the knowledge narrows. Finally, they just directly modify the corresponding various slots in the FFNs. In here, the T and T pipes just the word embedding of different 12 entities. And we can see that it just minor the values of the original entity and plus a large range of the change entity. And we can see its results. You can see that it seems can succeed in some case, but it's just a case study, and seems the change rate and success rate is very well. So it's just a good try. And then they also do some erasing. They also want to do another things, just erase the relations. We can see that this can use to protect someone's informations, right? Like some place of birth of someone's informations. So what they do, they first identify the related knowledge neighbors of the same relations in different entities. Then they retain 20 knowledge neighbors that appear most frequently, and they just set the value slot in FFN to 0. And they found that the capacity of the erased relations very increase after erasings. It seems useful, but we can also notice that other relations also increase a little. So let's draw conclusions. In this paper, it just proposed an attribution method to identify knowledge neighbors that express factual knowledge in per-change formats. And then they use suppressing and amplifying the activation of knowledge neighbors. They found that it can affect the exchange of knowledge expressions. It seems to work. And then they try to preliminary case studies. Knowledge neighbors to update or erase knowledge in per-change formats. So, and there are some limitations in these papers. They find that maybe the knowledge can be expressed in a more implicit ways, right? They just use quotes and let the model to predict the answers. But the knowledge may be stored in another way. What's more, they just focus on the factual knowledges. They didn't try other types of the knowledges. And it's interesting to find out how knowledge stored in the multi-language per-chain transformers. That's the end of my speech. Thank you.
You're gonna take that for the last part.
I think we can assume that it did the level with the I guess.
Okay, hello everyone. So I will talk about the topic about model editing, and today we will go through two papers which propose the method of model editing. So the first straightforward question is, why do we need model editing, right? Because we already know that the large language model is powerful to store a lot of knowledge and utilize it to accomplish many tasks. So the problem here is that actually, so I will explain it in the point of view of evolution. So we know that the world, there's so every day there are updated information, and in that case we also need to update the knowledge of the model to know that the world is evolving. And also as discussed by Hannah and the previous presenters, that we know that there are problems like the toxicity and the bias in the current model. So we also want to correct the such kind of errors and harmful behaviors of model to avoid that. So this is why we want to do the model editing. And another problem in the model editing is that actually we are
in lack of the enough data to full fine-tune a model to obtain the new knowledge. So in that case, what we want to do in model editing is that we want to enable the data efficient alterations to the behavior of models. So this is an overview of the existing methods of model editing. So we can generally categorize them into two types. The first one is we preserve the model's parameters. So in that case, we introduce additional neurons like this to train on the new knowledge data examples, or we just adopt an external model to like learn the behavior of what model should do when encountering new examples, right? And for the another type, we will directly modify the parameters of the current model. So this is what we want to focus in my today's presentation. So for this type of methods, we can also categorize them into two types. And the first one is about meta-learning, like we just learn how to tune the model parameters, like how to design the delta of the change of the model parameters to get an updated model. And for the second type is that we will just directly locate the modules in the current model regarding the knowledge we want to update. And once we locate such kind of models, then we directly edit it to get the new knowledge information. Okay, so in that case, we will cover two papers today, and one is for meta-learning and one is for locate and edit. So the first paper is about the method of locate and editing. And this paper just works on the specific domain of factuality. Yeah. So here is the basic intuition behind this paper, like why we want to edit the model architecture to update its knowledge. So the basic intuition behind this, I think, is the difference between knowing and the saying. So we can say that saying is actually something like a parrot-like behavior, right? Like the model just repeats what it observed in the training examples. But this is different for the knowing. So I think knowing differs in terms of two features here. So the first feature is specificity. So this means that given a new knowledge information like Eiffel Tower is in Paris, this should not affect the model behavior when it needs to like make judgment on unrelated knowledge, like Marine Park is in Singapore or something like that. And another feature is generalization. So this means that for the original knowledge information, we can actually have several alternatives or like paraphrasing that may have the entailed meaning or the similar meaning of the original knowledge information. But in this case, the model should make consistent judgment with the original knowledge if it is it understands the original knowledge. Yeah. So okay, with this in mind, then we can see how the paper proposed to do the locate and the edit to update the model knowledge. So I will illustrate the process using the figure here. So there are actually many shapes of different colors, right? And so the blue shapes here indicates the correct input, and output pairs indicating the knowledge we are interested in. And the yellow shapes here means that we will do something to corrupt the input tokens. And these corrupted inputs will lead to a also a corrected output, which is wrong in terms of the factuality. And then for the model architecture, we have purple shapes, red shapes, and green shapes representing the hidden states, the attention module, and the multi-layer perception models respectively. Okay, so with this architecture, what the paper proposes a method called causal tracing. So at the beginning, we have the correct input and the model architecture that leads to the correct output. And then we do the corrupted on the input data, and we get the wrong output, right? And what the paper proposes that in this case, we iteratively replace the current state with the original state that leads to the correct output. So at each time, we only select one single state to replace. And so we will run this process multiple times. And for example, at this point, we find that the subsequent information flow can lead to the correct output, right? So then we can say that for this state, the corresponding MLP module actually do the job of knowledge retrieval to retrieve the knowledge that we need to elicit the correct output, even we are provided with the corrupted input. So in this case, what the paper do is that they will like iteratively replace the restore the states and the states which is in the purple shape, and then in this manner they can find a set of MLP modules that can show the ability to retrieve the knowledge. Yeah. So now we know that we actually can utilize this kind of method to locate the place where the model has ability of knowledge retrieval. So the next research question comes to be, can we like do some things to just directly edit the module, and then we can directly update the model behavior when it needs to handle the new knowledge. So what the paper do also is that they also focus on the MLP modules to do the edit. So actually there are several terminologies we need to use to illustrate the process. So I will utilize the key and value, the pair of key and value to indicate a piece of information. And then the model behavior is that given the input, the key, for example, a subject, it needs to like elicit the knowledge about the subject, for example, the relation to other objects. Yeah. So this is the terminology we need to use. And then it's about the architecture of how we do the model editing. So this figure actually shows the architecture of MLP component. So we have the key here, which represents the subject, the input, and we have the model parameters we want to update here. And this function will actually project the inputs to the outputs, which is the value, the knowledge we are interested in. So what the paper proposed is that they define an objective here, and they want to make sure that given an ideal value and the representation of the input subject, we want to make sure that this updated parameters can project the input to the ideal output. So this is basically what they want to optimize. And what they did in the paper is that they need to like estimate the representation. They need to calculate the representation of the of one subject, and they will do that using different contexts and prompts, because they don't want to like overfit on the very specific examples of the knowledge. And they also need to like optimize the representation of the value here. So in that case, they need to both make sure that the key and value, they are corresponding to each other, like the information, the updated information is correct. And they also need to make sure that for the unrelated pairs, like the knowledge already learned in the model, the prediction should not be changed. Yeah, so that's the second objective to keep in mind when they get the representation of the value. So now they have the representation of the key and value, so they can just directly apply this objective to learn how to update the parameters of the weights here. Yeah, so this is generally how they do the edit part. So now this are the takeaways from this work. So I will just categorize them into two parts. So one is for the locate and another is for the edit. So for the locate part, we can learn from the process that at different position and different layers of the states. Actually, the states can sometimes retrieve the knowledge, and sometimes they cannot retrieve the knowledge. And what is observed in this paper is that the knowledge retrieval actually is usually done at the earlier stage, like in the middle layers of the architecture. And how the model works is that as the final layers, they utilize the mechanism like attention to retrieve this knowledge actually already retrieved in the previous layers. Yeah, so this is how things work if we want to locate the knowledge retrieval part. And another direction is how to edit the model. So this paper demonstrates that it's possible that just given one sample of the knowledge we want to update, we can utilize the edit method they propose. And this method can actually be generalized to the other scenarios. Like for example, here we say Eiffel Tower is in Rome, and if we do the model editing on the model, then the model is capable of answer the related question and give the answer consistent with the statement here. Yeah, so these are the main takeaways from this paper. So then we will go to another paper which work on the second direction to do the meta learning to update the model. So for this direction of work, actually there is a previous work which is about knowledge editor, and it will update the weights of the model for each data point. But the problems for this work is that it is hard to be applied and to work for the large language models. And differently for this work we will introduce today, it introduced some method which is data efficient and also parameter efficient, and that can be applied on the large language model. Okay, so this is generally the framework of their method. So they will utilize the information of one single example, and this single example will illustrate the model's error if it is not updated. And the main part of the meta learning and the model parameter update is here. So they utilize a collection of MLP models to calculate the delta, the the parameters we need to like alter from the original model. And in that case, we can utilize this output to update the model and get the output we want. So here again, there are several terminologies I need to introduce to illustrate the process. So actually, there are some ugly details from this paper, but don't worry, I will try to make it as simple as possible. Yeah. So here there are two models here. So the basic model is what we want to update. So they have input X and Y. So the theta here is the parameters of the model. And then we have another model, which is the model editor we need to train. So here is a loss function and as defined as this, and the phi here is the model parameters for this second model. And we want to utilize this model to gain a new set of models for the basic model, new set of parameters for the basic model. Yeah. Okay. So the ultimate goal here is that when given, new pairs of instances, we want the model to behave correctly. So if we give the model the in-scope samples, which means the examples related to the knowledge we want to update, then the model should directly give the correct answer corresponding to it. And also for the unrelated examples, which means the examples that's nothing to do with the knowledge we want to update, the model still need to maintain its previous performance. Yeah, so this is the two things we need to keep in mind. And then it's the core algorithm of this paper. So they are generally two parts here, and the first part, obviously we need to train the model editor, right? So to train the model editor, so you just need to keep in mind here we have the two targets. So we need to have a loss to learn the in-scope examples, and we also need a Khay diverging loss to maintain the behavior for the unrelated examples. So this is how we update and train the model editor framework. And then is the second part. So if we have the model editor, then how do we update the basic model, right? So here, while we do the iteration, is that there are many groups of parameters like the weight matrix W in the basic model. So we need to do the iteration on it. And because some of the weights may have different sizes, so different sizes will mean different, also different parameters in the model editors. So we will need to do the iteration to update the model. And then it's the key, one of the key ideas that I think is insightful from this paper. So we can say that the model needs to update the metrics of the basic model here, right? But the problem is that usually the size, the scale, the dimension of the metric is like D times D, the size. So this can be a lot of computation cost and time complexity. So what this paper do is that they do the factorization decomposition. So they go forward, they go backwards to how they calculate the weights or the gradients of the weights we want to update. So you can just remember this expression here. We need to utilize this function to get the gradient of the weights. And with this gradient of the weight and the corresponding input, we can just directly calculate the gradient of the weight with respect to the input. So in this equation here, the two elements, the delta and the u here, are actually two 1D vectors. So their dimension are both D. So in this case, if we just directly update these two vectors, then the cost will be reduced from the square of D to 2D, right? So this is how they ease the effort of the computation and makes it a more parameter efficient method. So what to do is that we can see that the network from the model editor, they just update this network and they get new U and delta from the original U and delta. So they can utilize this to then calculate the updated parameter of the basic model. Yeah. So this is generally what they do, and this is the figure to show how their method works. So you just need to pay attention. So here is the original input of the two vectors we want to optimize, and this is the output for the model editor. And they are owning two, so there's only one hidden layer. So they are owning two groups of parameters, right? So one is for this and one is the H2 here. So they only need to update these two groups of parameters in the model editor. And in that case, this means that different layers of the editor can share the parameters, and in that case, they also maintain the layer-wise visualization by using two additional hyperparameters to different layers. Yeah, so that makes their method more efficient. Okay, so to summarize, this paper proposed a meta-learning way to update the model, and what they do, what's their core contribution is that they utilize low rank weight matrices to do the to utilize the factorization of the gradient to propose a parameter efficient way. Yeah. So okay, and then there is a table to compare the different model editing methods. So we can see the two papers we go through today, the Rome, the first paper, and the second paper. So we can see actually the first paper, it will get more significant improvement in the performance, but we can see that for this criteria, generality, it is relatively low than the other two criteria. And also another thing to mention is that even although Rome has a better performance, we can see that it will actually cost a lot more than the meta-learning method. Yeah, so this kind of like a trade-off between the performance and the cost. Okay, so then is some open problems I think might be very interesting in the domain of model editing. So from these results, we can see that the generalization is still the model is it has the deficiency, and so there is actually an example to illustrate this problem. So like if we have the original knowledge we want to update, and then we give it another pair of related knowledge, but they are actually different. But the model may have the performance of overgeneralization, and it will repeat the output of the previous knowledge. Yeah, so in that case, one thing to mention is that we may work on the dataset part, like we need to increase the quality of the data we use to tune the model. And in that case, we may either work on the equivalence neighborhoods creation. So this is to assess and tune the model editor in the model editing methods. And another way is that we work on some counterfactual data augmentation. And then we can both increase the difficulty and the quality of the data. And another direction is that actually both papers in today's presentation, they both work on the factuality, but actually there are a lot of more domains we are interested in, like the toxicity, like the social bias. Yeah, so maybe we can also apply this method to many other domains and see how they work. Okay, that's all from my today's presentation. So, yeah, this is an overview of our today's presentation and some related links that might be useful. Yeah, thank you.
Again, let's thank all of our speakers today. They did a great job of having a lot of notes and presentations where people could be here. Okay, and because we didn't intervene too much and asked lots of discussion questions, we're able to finish at a reasonable time. I hope you enjoyed your mooncake. There's still 2 more slices, so that's it for today. So we'll come back next week. Yeah, sure. Thank you, everyone.
Stop share.
Just a note of reminder that your second sprint is due, so you need to go back to your slides and add that one slide from the second sprint. Okay, you're not sure whether you can make all of your deliverables. That's okay. You have to let us know. That's the important part. So if you haven't met with your project team, if you're doing it not just with a single person, please meet with your project mates update. Okay, thank you.
I'm not used to the how things are on the Mac.
Yeah, no worries.
Okay, cool. Thanks.
Thank
Thanks for the
you.
mooncakes.
Yeah, sure. There's still 2 more, so please finish them up if you're interested. Just take it.